Okay, so right, so a matrix tree theorem in higher dimensions. And of course, I have to now reset my Zoom does not interface well with the preview on the Mac, I've decided. So here are my two collaborators again. There's Professor Vladimir Cherniak from the Department of Chemistry and Mike Catanzaro, who is no longer at the University of Florida. That's a typo. He is now at Iowa State. I copied that slide from somewhere else. And what we did this work when Mike was at the University of Florida. Mike was a student of both of ours. Okay, so I'm going to start off talking about simplicial complexes, and I'm going to define all these different terms. And in the second part, I'm going to talk about the higher matrix-tree theorem, and then I'm going to mention some things about the proof. Okay, so let me get started. So in this talk, we have a fixed set, which will be a universe. And there's some huge set that we know nothing about, but it doesn't need to be huge, but typically it's a huge set. A simplicial complex is a collection of finite non-empty subsets. So you have a collection of finite subsets of the universe. So here it is. It's a collection, the sets are called sigma. They're finite and they're indexed over an indexing set I, and that's what X is. And the only condition you impose is that the collection is closed with respect to taking inclusions. That is, if you have an element of X, this collection of finite sets, and you have a subset of sigma, then that subset is again an X. That's all that you demand. That's what a simplicial complex is. So a simplicial complex is a combinatorial object. It's just a collection of sets, finite sets closed or under inclusion. And this is really what's called an abstract simplicial complex as opposed to a geometric simplicial complex. Okay, so what do simplicial complexes do? They're supposed to model, give a combinatorial model for topological spaces. But before I get into that, let's say that X is finite if the indexing set I is finite. Okay, so in this talk, we're only going to talk about finite simplicial complexes. So there's a finite collection of finite subsets of the universe. Each element of X is called a simplex. And we define the dimension of a simplex to be the cardinality, one less than the cardinality of the set sigma. So the dimension of sigma is one less than its cardinality. If the dimension is k, is that a number k, we call sigma a k-simplex. And we'll write x sub k for the set of all k-simplices. So sometimes we resort to graph notation. We'll call a 0 simplex a vertex, and a 1 simplex will be called an edge. And note that a 0 simplex is just a singleton subset of X. It's a set with a single element, because the number of elements in sigma, if sigma is a vertex, has to be 1. And likewise, an edge has 2 elements in it. We'll write dimension of X is D. The dimension of the simplicial complex is D if X has a D simplex, but there are no simplices of dimension greater than D. Okay, so these are the basic definitions. And I just want to point out something which we don't really use so much, is that a K-simplex is completely determined by the set of all its vertices. See, a K-simplex is a set of K plus 1 elements of the universe, right? And it's in X, but it's as a set, it has K plus 1 elements. And so we can look at all the 1 element subsets of it, and those are the set of vertices of that K-simplex. And so you get a function which goes from the set of K-simplices to the set of subsets of the vertices of cardinality K plus 1. and that's a function, and that function in a simplicial complex is obviously one-to-one, if you think about it for 3 seconds. This is a one-to-one function. So what I'm saying is that a K-simplex is determined by its vertices. Okay, here's an example that you've already encountered. The example is that if you have a one-dimensional simplicial complex, that's something which involves vertices and edges, then that's a simple graph in the sense of the previous two talks. That is, it's a graph with the property that any pair of vertices has at most one edge connecting them. So a dimension one simplicial complex is a graph. Oops, and now I've lost my, this is really buggy. Okay, so if the universe is a finite set with n+1 elements labeled 0 through n, then the set of all non-empty subsets of that universe, which is just a set, sort of a standard set with n+1 elements, is a simplicial complex of dimension n, because you could, this is sort of the complete simplicial complex on U. And there are no n+1 simplices or higher because there are no subsets of, oh, this is, am I saying this right? Yeah, there are no simplices of dimension n+1 or higher because there are no subsets of cardinality n+2 or more. Okay, so great. And so this is called the standard n-simplex, and we denote it by delta n. So that's the standard n sub. It's a set of all subsets of the standard set 0 through n. The D skeleton is given by the set of X is given by the set of all simplices of dimension at most D. So you throw away all simplices of higher dimension. And that is now, if we take the D skeleton of X, you get a new simplicial complex, but that simplicial complex has dimension D. Okay, so a very important simplicial complex is the n-1 sphere. It's called the simplicial n-1 sphere. It's the n-1 skeleton of the standard n-simplex. So you throw away the single, so the delta n has a single n-simplex, which is all of the universe U in this case. So you throw away that top dimensional simplex and you're left with what is called the simplicial n-1 sphere. And here's a picture. So here's the standard 3 simplex. So the set of vertices are the set of subsets of cardinality 1. I've listed them there. The set of 1 simplices are the set of subsets of cardinality 2. So when I write 0, 1, I mean the set consisting of 0 and 1. So there are exactly 6 edges, or 6 1 simplices. There are 3 2 simplices indicated by 0, 1, 2, 0, 1, 3, and 1, 2, 3. And there's exactly 1 3 simplex. And if you draw you can indicate this by a picture where, for example, the 2 simplex that 1 2 3 is indicated in dark gray in the picture. And if you throw away the top dimensional simplex, you kind of think of you're throwing away the interior of this tetrahedron, and what's on the outside, the boundary, is like a 2-dimensional sphere, right? So that's why we think of it as the simplicial. So the boundary of this geometric 3 simplex is a 2-sphere. X is said to be connected if it's 1 skeleton. Now that 1 skeleton is a graph, right? So is connected in the sense of graph theory, which means that any pair of vertices is joined by a path of edges. Okay, so it makes sense to talk about connectedness of simplicial complexes. So all this means is if you just ignore everything but the vertices and the edges, that graph is a connected graph. Okay, so now it's important in this talk to use ordered simplicial complexes. So what is an ordered simplicial complex? Well, by the well-ordering theorem, we may assume that U is equipped with a linear order, right? So that you can compare any 2 distinct elements of U by the ordering, right? Once this has been fixed, we'll say that X is an ordered simplicial complex. And the advantage of an ordered simplicial complex is that there are these face maps. So if you have an n simplex, there are n plus 1 face maps which assign to an n simplex an n minus 1 simplex. And how is it defined? Well, if you take an n simplex, that's a collection. That's a set with n plus 1 elements, which now we can view as being totally ordered, because we're in an ordered universe. And now we can throw away any of the 0th element of sigma or the first element of sigma. So we just remove it, and there are n plus 1 maps we're defining in that way. So if we remove I sub k from sigma, we get a set, an ordered set, in fact, with n elements, and that's an n minus 1 simplex. And here we've used the property of being a simplicial complex, because if we remove an element, it's closed under taking away elements, right? So this face map is well defined, and there are n plus 1 of them for on the set of n simplices. These maps satisfy the commutation identity, or the commutation rule, that if we take away, if we take di composed with dj, that's dj minus 1 composed with di if I is less than j. Roughly speaking, when you take di dj, you're removing 2 elements from your set of n plus 1 elements. And if you remove 2 elements, you can think of how, if you remove one, the first, say, one of them, then the one remaining, you have one remaining, that changes its index in the ordering. And that's what's going on here. So that's why this commutation rule holds. Very important rule. So this is used. So now I want to talk about chains. So let's fix a commutative ring. Let's call it A in this talk. And in this talk, A is either going to be the real numbers or the integers and nothing else. So either the real numbers or the integers. So a module over this ring is either a vector space or a Z module, which is an abelian group, right? But so a K chain on X is going to be an A linear combination of K simplices. That's what a K chain is. It's an A linear combination of K simplices. So if A is the real numbers, you're just taking a linear combination over the reals of K simplices. And in the other case of the integers, you're taking an integer linear combination. So let's C sub K be the, well, in complete notation, C sub K of X semicolon A be the free A module having basis X sub K, right? So it's a free module over A. So in the case where A is the real numbers, that's just a vector space. And in the case where A is the integers, it's just a free abelian group. And the basis is the set of K simplices. C sub K is called the group of K chains, and it's an A module. And note that C sub K is 0 if K is bigger than the dimension of X, because if you're bigger than the dimension of X, there are no K chains. Now we get to the chain complex. The chain complex is a sequence of homomorphisms. So it's just a string of mapped homomorphisms, C sub K to CK minus 1 to CK minus 2 in this way. And, it goes on. And here's the formula for it. If you're given a K simplex, the kth boundary homomorphism from CK to CK minus 1, you apply to a basis element, is given by the alternating sum of its faces. So I'm taking the alternating sum of all the faces. Okay, so that's the definition of the kth face operator. And what this is geometrically doing is, if you go back to my picture of the 3 simplex, it's sort of taking an algebraic version of that, of taking the boundary of that 3 simplex, because each face d sub I of a 3 simplex is a 2-dimensional face, right? And you're taking a kind of signed sum of all those 2-dimensional faces. So here's the crucial property of these boundary homomorphisms. If we compose any contiguous pair, we get the zero homomorphism. So I'm going to give you a proof of that. This is an important property. The composition is given by the following expression. So it's the summation of alternating sums of face operators composed with itself. And then we can rewrite this because when you take I and j, the first sum on the left is indexed over I, and the one on the next summation on the left is with j. So we can break it up into I less than j and I greater than or equal to j. And that's what I've done on the first line in the display on the right. But I've written the stuff with I less than j in blue and the stuff I greater than or equal to j in orange. And the reason I do that is then I go to the next line of display, I don't do anything with the blue summation, and I rewrite the orange stuff in the following way. I re-index. And how do I do the re-indexing? In the above, the orange sum has been replaced by the red one by re-indexing. I just renamed j as I plus 1. I just renamed it. So I substitute the change in, and I get the red expression in place of the orange expression. And now I just, for I less than j, I'll use the commutation rule to cancel the term minus 1 to the I plus j di dj with the corresponding red term on the right-hand sum. And that cancels, and there's a one-to-one cancellation. Everything cancels on the right, so you get 0. So that's why the composition of boundary homomorphisms is 0. So that's a crucial property. Any questions? Okay, some of you have seen this. If you've had some topology, algebraic topology, you would have seen this already. Okay, so when K is understood, we drop the subscript in the boundary homomorphism and just write boundary instead of boundary K. I'm getting rid of clutter here. That's the whole, that's the point. So the group of K cycles is the kernel of the Kth boundary homomorphism, and that's a submodule of the K chains. In the case of A being the real numbers, this would be a vector subspace. So I'm taking the kernel of this linear transformation in that case. The group of K boundaries is the image of the K plus first boundary operator inside the K chains. So that's called B sub K. So we have Z sub K and B sub K. And if you were at my talk last week, that should remind you of what I did last week with graphs. And because boundaries squared is 0, BK is, the boundaries are contained in the cycles. That's obvious now because boundary of boundary is 0. So we could ask the question of how far do the boundaries deviate from being cycles, right? How far do the cycles deviate from being boundaries, I should say? And the answer is we measure it in the following way. We take the quotient space, or the quotient, in the case of the real numbers, of the quotient to be the quotient module, zk quotiented by bk, and that's called the kth homology group of X with coefficients in A. And it turns out, by what I did last week in my talk, that the dimension as a vector space of H0 of X with coefficients in R is 1 if and only if X is a connected simplicial complex, because X is connected if and only if the one skeleton, which is a graph, is connected. And we saw last week that, or I mentioned at least, I actually gave a sort of a proof that the graph is connected if and only if H0 is equal to 1. Okay, so its dimension is 1. Okay, so here's an example of the homology of the two-sphere. Remember, the two-sphere is comes from the simplicial 3-simplex by throwing away the top dimensional simplex. So here are the vertices, edges, and faces of the two-sphere written out for you. I don't have a 3-simplex anymore. And so as a vector space, if we do this with coefficients in the real numbers, I have a basis of 4 elements for the vertices, so it's R4, and then I have R6 for the one chains, and the two chains are isomorphic to R4. And I can compute the boundary operator explicitly because it's an alternating sum. So for example, let's look at the first column. This is supposed to be the boundary operator from the two-dimensional chains to the one-dimensional chains. And how did I compute this? Well, let's look at the first column. The first column is the effect of applying the boundary operator to the first basis element of the two simplices, which is 0, 1, and 2. Now, if I take the boundary of 0, 1, and 2, that means I have to delete a single element, and there are signs involved. So if I delete 0 from 0, 1, 2, I get 1, 2. And 1, 2 is the matrix entry, which is, did I do this right? Let's see, 1, 2 is the matrix entry. Let's see. Oh, yeah. So 1, 2 is the fourth entry of x1. So that, and it has a sign of +1 according to the way I define the boundary operator. So I go into the first column and the fourth entry is indeed +1, right? So that's where I get the +1 in the fourth entry of the first column. And likewise, if I remove 1 from 0, 1, 2, I get 0, 2, and that's the second entry, but it gets a minus sign in front of it. And you see the second entry in the first column is -1. And lastly, if I remove the 2 from 0, 1, 2, I get 0, 1, but that's the first entry and it has a sign of +1. So that tells you why the first column is what it is. And likewise, I can compute the boundary operator from the 1 chains to the 0 chains, and this is what you get. And from this, you get explicit matrices you can compute with. And using Gaussian elimination, you can see that the rank of the first matrix, boundary 2, is the same as the rank of boundary 1, which is 3 in both cases. And from this, it's not hard to calculate the homology, because the homology is a quotient vector space in this case. And I'll leave it to you to work out the details, but this is the answer. The homology of the two-sphere with real coefficients has dimension 1 in degrees 0 and 2, and it's trivial otherwise. So that's the homology of the two-sphere. In particular, the second homology of the two-sphere is 1. And this is what people often say about homology. It counts holes. The ith homology counts I-dimensional holes in your space. So if we had done this with the n-1 sphere, we would have gotten homology in degree n-1. The calculation would be very similar, but a little more tedious. Okay, so we've just computed the homology of a two-sphere, just linear algebra. Okay, so now there's something called relative homology, which I'm going to need in this talk. So if you have a subcomplex, you can you can look at the chains relative to L. It's called the chains relative to L with coefficients in A. And what you do is you just take the free A module, not with basis the K simplices, but you remove all the K simplices of the sub-simplicial complex. So you remove the K simplices of L from the K simplices of X. And it has the same boundary formula for the boundary operator works here. It's the same definition. So I won't write it down. It just works the same exact way. So you get a chain complex called the relative chain complex. And I've suppressed the coefficients. It's the same coefficients in A. These are A modules, free A modules. The relative homology is again defined in the same way, but you work with the relative complex. It's the cycles divided by the boundaries. And okay, so that's what I wanted to say about homology. Now we get to spanning trees. So in my last week's talk, I defined spanning trees for graphs. Now I'm going to define higher dimensional spanning trees in a simplicial complex. So what I'm going to do is I choose some integer any integer you hand me, let it be called D, that's sandwiched in somewhere between 1 and the dimension of my simplicial complex. A spanning D tree for X is a subsimplicial complex T of dimension at most D, such that the d minus 1 skeleton of T is exactly the same as the d minus 1 skeleton of X. It has the same simplices in dimensions d minus 1 or less. So there's nothing new in dimensions d minus 1 or less. The top dimensional homology of T vanishes. The top dimensional homology of T vanishes. That is the d-dimensional homology. And the last condition is the dimension of the homology with coefficients in the real numbers in degree d minus 1 of T is the same as that of X, right? That is, there's no change in the d minus 1 homology. So this is, if you saw my talk last week, this is one of the ways I defined a spanning tree in a graph, if you go back. Okay, so this is actually sort of the same definition translated to higher dimensions. If d equals 1 equals the dimension of X, this coincides with one of the usual definitions of a spanning tree in a graph. It was my second definition. The first person to define spanning trees in higher dimensions was Kalai. I actually know him in 1983, but he was only concerned with a very special case where the d minus 1 skeleton of X was a simplicial d minus 1 sphere, which the same thing we defined before, right? So he was only considering this case. He did not have a definition which worked. With his definition did not work for arbitrary simplicial complexes. The above definition is actually due to us in 2015. However, there are equivalent variants due to Richard Lyons, and then there's three authors, Duval, Clivens, Martin. So that's Art Duval, Carolyn Clivens, and Jeremy Martin in 2009. So this is not really due to us. It's just the flavor of the definition is due to us. And these other authors didn't even really work with CW complexes. They work with we generalized it. We're working only with simplicial complexes today. So our definition works in greater generality. Okay. So here's an example of a spanning tree. So I'm going to take the 3 simplex, and here's how you get a spanning 2 tree. You remove the 2 simplex from the 3 simplex. So what you do is you take the simplicial 2 sphere. That's the 2 skeleton of delta 3. And remove the 2 simplex. Oops, that's not good. That's the 2 simplex is given by the set 1, 2, 3. Remove that face from the sphere, and what's left over is a 2-dimensional simplicial complex that has 3 2-dimensional simplices indicated by 0, 1, 2, 0, 2, 3, and 0, 1, 3. So I've just removed one of the faces of the surface of the tetrahedron, the face given by 1, 2, 3. And that turns out to be a spanning 2 tree in delta 3. It's a 2-dimensional spanning tree in delta 3. So here's here's a lemma, which is analogous to a lemma I proved last week for spanning trees in a graph. For a given X, the set of spanning D trees is non-empty and finite, okay? In fact, it also exists. There are spanning D trees. So by replacing X by its D skeleton, we can assume that the dimension of X is D. So let sigma be a D simplex. Remove sigma from X to give a new simplex. This is a recipe. So I'm saying remove sigma from X to give, we can assume X is D dimensional by just throwing away everything above dimension D. Remove any top dimensional simplex. That'll give you a new simplicial complex, call it Y. And we'll say sigma is essential if the dimension of the homology in degree D minus 1 does not change. Okay, we need that condition, remember, in forming a spanning tree because that was one of the axioms in the definition. Otherwise, we'll say sigma is inessential. That means that the dimension of that homology group changes. So let's assume sigma is essential. Then it's not hard to show that the dimension of Y in the top dimension changes. So dimension actually changes if you remove an essential simplex, it goes down. We then iterate the procedure, do this with y, and just keep going, repeating it, take away a simplex from y, an essential simplex from y, to get another simplicial complex, and keep going until the process stops. At some point, it has to stop. And the result actually will be a simplicial subcomplex, which is a spanning D tree, because the dimensions of the homology will have to be at a minimum, and it's not hard to show with a little bit of effort that what you get is no homology in dimension D. So this is the proof. It's very similar to the proof I gave last week, which shows that spanning trees in a graph exist. Okay, so from now on, let's assume that if you look at this proof I just gave, I threw away all the higher simplices above dimension D. So we might as well assume from now on in everything I do, it doesn't change anything really, it just makes it simpler to discuss. We may as well assume the dimension of X is actually D itself, the number D itself. So when D is understood, we'll call a spanning D tree a spanning tree. I just want to simplify language here. So we could talk about a spanning tree in a simplicial complex of degree D is a spanning D tree. And so from now on, X will always have dimension D. Hold on one second, guys. I have to answer a call. Sorry about that. So anyway, I want to talk about something next. Oops, I lost the, that's great. This is the pitfalls of working at home. So, okay, that sucks. Let's see, I will go back to full screen. Okay. So, anyway, so we're assuming, so we have the notion of a spanning tree, which is just a spanning tree in a simplicial complex of dimension D. And I want to talk about something called the spanning cotree. That's sort of a dual notion. So we'll continue to assume that D is the dimension of X. And there is a definition. It's not phrased in this way in the paper of Lyons, and we thought we discovered this independently. It was hard to figure out what Lyons was doing. He works with matroids, and I don't even know what a matroid is exactly. So a spanning cotree for X is a simplicial subcomplex in X, L of dimension at most D minus 1. So it's not the top dimension, it's one dimension less, such that the D minus 2 skeleton is the same as the D minus 2 skeleton of X. The homology in degree D minus 1 is an isomorphism. So the top dimensional homology of L is the same as the top dimensional homology of X over the real numbers. Not the top dimensional homology of X, I mean the D minus 1 homology of X. That's not the top dimension, but the penultimate dimension. And the dimension of the D minus 2 homologies coincide. Okay, so these are the three conditions of a spanning cotree. So in a spanning tree, the top dimensional homology of L would have been 0, but we're now assuming that the top dimensional homology of L coincides with the homology of X in that degree. That's the difference. And the other difference is we're working in dimension D minus 1. So with X as above, there exists a spanning cotree L and X, Moreover, the set of spanning cotrees is finite. So they exist and they're only finitely many. By the way, the finiteness just follows from the fact that these are subcomplexes and there are only finitely many subcomplexes since there are finitely many simplices. So that's where the finiteness comes from. But the existence is the more interesting thing. And I won't prove it, but the proof is along the lines of how we proved a spanning tree exists. It's a very similar proof, and I'm not going to bother to give it. Okay, so spanning cotrees always exist. And here's the a lemma. If D equals 1, then a spanning cotree, which is something which, remember, is a subcomplex in degree 0 in this case, is the same thing as a vertex, a zero simplex of X. And why is that? Because in this case, a spanning cotree is a connected zero-dimensional subgraph of X. And it's a zero-dimensional subgraph. That is just a set of vertices. And the only such set of vertices which are connected are singletons, that is zero simplices. And so that's a vertex. So therefore, a spanning cotree when D equals 1 is just a vertex of X. Okay, so we've just generalized sort of by means of homology what we mean by a vertex in a graph to higher dimensions. That's what this effectively does. Here's a picture of a spanning cotree when the dimension is 2. Here's a two-dimensional simplicial complex. What I've done is I've taken the set of vertices is 0 through 5, and the stuff in green are all the one simplices and the two simplices. So there's no two simplex of the form 3, 4, 5, but there is a two simplex labeled 0, 3, 5, for example. Okay, so this is a two-dimensional simplicial complex. I want to write down a spanning tree, a cotree. So that's a one-dimensional subcomplex. And so what is it? Let's look at the stuff I've just colored in red. That's a one-dimensional subcomplex. That is a graph inside there. It consists of vertices, all the vertices 0 through 5, but it has only we've removed the and there are no two simplices, and we removed the edges in green. There's no edge labeled 0, 5, 1, 3, or 2, 4. And so here it is. This is actually turns out to be a spanning cotree. You can check the conditions that it actually is. Its one-dimensional homology agrees with that of the original picture, but that's a computation. Okay, so there you go. And now I want to introduce now some numbers which are crucial to the main theorem, which don't appear when we were talking about the matrix-tree theorem for graphs. So first of all, if I take the D minus first homology, that's, remember, X has dimension D, we can take the D minus first homology of X with integer coefficients. Now that's an abelian group. It's a Z module, so it's an abelian group. It may or may not be free because it's a quotient group, remember? So it might have torsion, but it's finally generated torsion. So you can ask what the order of the torsion group is, right? How many elements are in the torsion subgroup of that homology group, and that's called theta X. Okay, so that's theta X. Likewise, we can do this for a spanning tree. We can do the same thing. We can take the order of the torsion subgroup of HD minus 1 of T with coefficient Z. Now, it turns out because HD minus 1 of T with coefficients in R vanishes, it turns out that, because it vanishes, it turns out that group, the D minus first homology of T, which is the top dimensional homology of T with Z coefficients, is a torsion group. It turns out to be entirely torsion. There's no free part of it. So we could just take the order of the entire group, and that's called the tree number of T. It's the order of the top dimensional homology with integer coefficients. And then lastly, we can do something for a spanning cotree. We can talk about the cotree number. That's called A sub L. And that's the order of the top dimensional relative homology of X relative to L with integer coefficients. So we have three kinds of numbers. We have a theta X, the order of the torsion subgroup of the D minus first dimensional homology of X, integer coefficients. We have theta sub T for a spanning tree, defined similarly. And then we have A sub L, which is the corresponding thing for relative homology for a spanning cotree. So that's called the cotree number. Okay, so we now get to the main theorem. Let X be a simplicial complex of dimension D, I want to consider. Oops, again it happens. Oh, here we go. I figured out what's going on. Okay, so the restricted Laplacian is a composition of the boundary operator on the right, from the D simplices with real coefficients to the D chains with real coefficients to the D minus 1 boundaries of real coefficients. And then what I do is I take the transpose or the formal adjoint boundary star. That's also called the co-boundary operator by some people, right? So we can take the composition of boundary with boundary star, which is then going to be a self-linear transformation from the D minus 1 boundaries to itself. And that's called the restricted Laplacian. It's a linear operator. And the higher matrix-tree theorem is the following statement, that the determinant of the restricted Laplacian has the following expression, which involves tree numbers and cotree numbers. So T here is going to range over all spanning trees. L is going to range over all spanning cotrees. And for each L, each spanning cotree, you take the cotree number. And for each T, you take the corresponding tree number. And then there's a prefactor in that product of sums, which is theta x squared, 1 over theta x squared. And I think I got this right. I think I got the way I've expressed this correctly. I might have gotten something else wrong. There might be squares. I have to check that out. This might not be stated exactly correctly. I might have to take the square of A sub L and theta sub T to make this make sense. What do you think, Vladimir? Doesn't it have to be squared?
I don't remember all this.
Yeah. But the point is that this is all the information you need to get the determinant of the restricted Laplacian. And I might have to correct that statement later. Okay, I can look it up. Anyway, so I want to make some points about this theorem, which is due to us in 2017. When D equals 1, we obtain the usual Kirchhoff matrix-tree theorem because all of these tree and cotree numbers are 1 in that case. There's no torsion. That's the reason. So the order of these groups is just the trivial group, and that has order 1. And the other remark I want to make is our theorem is not stated anywhere else, except that it turns out, and this was work on our part, it's non-trivial equivalent to a formula, which I call an asymmetrical formula due to Lyons in 2009. So Lyons has, at the end of his paper in 2009, some strange formula, which he calls a matrix tree formula. We didn't notice this until after we wrote our paper, but it looks nothing like this. And through effort and some effort, like 2 pages of work, we were able to show our formula was equivalent to his, but it was non-trivial. Okay, and then our work generalizes results of Kallai and Duval, Clivens, and Martin. So they do something different. Again, they have Duval, Clivens, and Martin have an asymmetrical formula, I believe, as well. So I'm not sure. Anyway, so we generalize I mean, those results. And our result is the most symmetrical result out there. It's the role of spanning cotrees and spanning trees is the same. Now, if you think about it, what does this have to do with the matrix tree theorem? Well, L, in the case where D equals 1, L is a vertex and T is a spanning tree in a graph. And all of the tree numbers and cotree numbers and the prefactors are 1. So what is the sum of ones over all the vertices? That's the number of vertices. What's the sum over all trees? That's the number of trees, right? So that's why it's a matrix tree theorem. Okay, so here's an example of a calculation. By brute force calculation, the simplicial complex S2 has 4 spanning trees. What I mean by a spanning tree, again, is a spanning two tree. Given by removing a single 2 simplex from the 4 faces of the tetrahedron, right? We saw that, or at least claim that when I remove a face from a tetrahedron, I get a spanning tree. And there are 4 possible ways of doing it. And those are all the spanning trees, 4 of them. There are 16 spanning cotrees, each given by removing 3 of the 6 edges of S2, of the one skeleton of S2, such that there are no cycles in the resulting one skeleton, right? You don't want cycles in the one skeleton because you need H1 to vanish. Moreover, in this case, the tree and cotree numbers are 1 because there's no torsion. So what we get by applying the theorem is the determinant of the restricted Laplacian is 4 times 16, which is 64, right? So this gives you a much easier way to compute the determinant of the restricted Laplacian. It's a rather large matrix. Okay, so I mean, you know, you have a huge number of, it's not easy to calculate the Laplacian. First of all, there's no obvious basis for the boundaries that you can use. Okay, so there you go. Here's another example, which I'm not going to compute. I want to point out that you could get torsion. So here's a picture of what is called the projective plane. It's a simplicial decomposition of the projective plane. It has 6 vertices, 15 edges labeled in the picture, and 10 two simplices. Now, the picture is drawn in such a way that the edge labeled 1 and 2, 1 to 2, there's two edges that are labeled 1 and 2, but they're really one edge. I make an identification of the two edges labeled 1 and 2 in the picture. And likewise, 2 and 3 are identified in the corresponding way. And so you make all the identifications as indicated by the picture, right? And there are 2 such identifications. And then if you do that, it turns out that the torsion, there's torsion. The homology in degree 1 of the projective plane is with integer coefficients is cyclic of order 2. That's what this is saying. So you can get torsion, so you get fractions in the answer possibly for the determinant of this Laplacian, or you know, it's potentially the case. Okay, so the rest of my talk today, I'm going to mention not all the proof, but one element of the proof, which turned out to be extremely useful. And it's something we discovered quite by accident. We gave a different proof of this kind of theorem before in another paper in a way. And then we improved it. And the real sort of kind of useful thing was something called least squares, which is something that people do in statistics, in fact, right? So here's a very general sort of problem you can ask. It's called the least squares problem. Suppose I'm given a linear transformation, call it A, although I've used A for a commutative ring, but now A will be a linear transformation from Rn to a finite dimensional inner product space V. Now, you may want V to be based, have a basis, but we need to get away with something less than a basis, and that's called a lattice. A lattice is sort of not specifying a basis, but specifies the free abelian group inside the vector space that the basis generates. So a lattice is a free abelian group inside V, which has the same rank as V, right? That's the, that's all a lattice is. So let B be any fixed vector. It's data that you start out with. You have a vector. And the problem, the generalized least squares problem is this. I suppose I have a linear equation, ax equals b. Now, a may not be one-to-one and it may not be onto. There's no reason to believe at the outset that ax equals b has a solution. But maybe we want to sort of find the closest thing to a solution. So let's find x in Rn, a vector, subject to the following two constraints. The first constraint is I like ax minus b to be a minimum in norm, right? I would like it to be norm minimizing, right? So I like to minimize the norm of ax minus b. So if the norm were 0, I would have a solution, right? The second condition I want to impose is the norm of x itself is minimizing among all solutions, among all sorts of, all x's which satisfy condition 1. So if I have something satisfying condition 1, I want also the norm of that thing which satisfies condition 1 to be minimizing. Okay, so classically one only considered the injective case. A is an injective homomorphism. So what that means in that case, you can see that in the injective case that well, it turns out the second constraint is not important. It goes away. So we just care about the first constraint, ax minus b, being norm minimizing, right? We don't care about the second condition involving x when a is injective. Because there's only one solution, right? If a is injective. So the norm x being minimizing is automatically holding in that case, if a is injective. Okay, so now that's the injective case, and we're really not interested in this classical situation, it turns out. We're interested in the dual case. We're more interested in the case when A is surjective. So that's the other constraint. So find this unique solution to the equation. Now there are solutions because to the equation. Ax minus b will have norm 0, right? That's a minimum, such that the norm of x is actually minimizing. Okay, so I'm looking for a solution which has x, which has minimal norm. So here's how you solve this equation. So let's choose a subset of the numbers 1 through n. So n will be the dimension of, n was the dimension of the domain of our linear transformation, right? So remember, A is a surjective homomorphism, so the dimension of V is at most n itself, right? It's not larger than n, right? And so let's look at a set these are sort of going to be the columns of our matrix, if you like, 1 through n. So let's choose a collection of columns. How many columns? As many columns as the dimension of V. Okay, and let A sub S be the composite homomorphism. I take the vector space on S. I'm just looking at the set of the vector space spanned by those columns of A. That's all I'm doing here, and that's what A sub S is. It's the vector, so it's basically restricting A to the column space, the subspace of the column space defined by S, and that's A sub S. And I only consider those S's in which the determinant of A sub S is non-zero. A sub S here is a square, if V was based, would be a square matrix, right? So it's a linear transformation between vector spaces of the same dimension. So we can talk about its determinant. By the way, its determinant is not exactly well defined, but it being non-zero is well defined because we only have a lattice. We don't have a base. We don't have a basis. If we had a basis, the determinant would be well defined. Okay, so then what do I say? What am I saying? Yeah, no, I'm wrong here. The determinant is well defined here. Well, no, the determinant of AS is not well defined, but its square is well defined. Let me backtrack. If you have a lattice, it turns out that the determinant is not well defined. It's only well defined up to a sign. And so we can square the determinant, and that is well defined. So let's take the square of this determinant, and let's call that T sub S. Okay, so I'm saying things from linear algebra, which you may not be aware of, but you can check this is true. These are exercises in linear algebra. I'm saying that if V does not have a basis, but only has a lattice, then you can still take the determinant of A sub S, and it's defined up to sign. Okay, that's what I'm trying to say. Okay, so then the solution of my original least squares problem is given by the following notation. It's A plus of B, where A plus is the following linear transformation. I take the inverse of A sub S, which is a linear transformation from V to RS, the vector space RS. And then I include back into Rn, so that gives me a linear transformation from V to Rn. And then I multiply it by T sub S, that operator. And then I sum up over all choices of S, so I'm averaging. And then I have to normalize by the sum over all these T sub S's. So this should remind you again of like my talk last week vaguely when I computed the projection of my one chains onto my one cycles in the matrix-tree theorem. This is very similar to that, right? This kind of sum that appears. Okay, so this is what you get, and this solves the least squares problem. And this turns out to be like a main ingredient in our proof. So this formula, you would think that this was old, right? I mean, this is like kind of, stuff people could have been talking about in 1900, right? But we could not find any mention of this formula. We discovered it. It came from the 1980s and is independently due to Berg and Ben Tal and Tubui published in 1990. So the formula, I could not find a statement of this formula prior to the 1980s. But in really what it is, it's a version of the so-called Cauchy-Binet theorem. It's sort of a summation version. It's a variant of Cauchy-Binet. That's probably the best way to say it. By the way, this A plus operator is an orthogonal projection. That's really what you're getting in this case. You're getting or an orthogonal splitting of the matrix of the linear transformation A. So you're basically splitting the projection of Rn onto V. You're writing Rn as V plus something else orthogonally. Those works though, this formula from the 80s only considered the injective case, which was the classical least squares, but the surjective case can be deduced from the injective one. That's what we did in our paper by just taking transposes of everything, because transposes turn injective linear transformations into surjective ones. Okay, so how least squares is applied to our situation, let me just give you very roughly what we did. It's applied to the quotient homomorphism from this d minus 1 cycles to the d minus first homology. That quotient map is a map of vector spaces. HD minus 1 remember was ZD minus 1 divided by BD minus 1, the boundaries. And so least squares can be used, if you think about it, to actually split this homomorphism to and it'll give you an orthogonal splitting to the inclusion. So you're writing the d minus 1 cycles as the d minus 1 boundaries orthogonal direct sum with the d minus 1 homology. And that's sort of how it's used in the matrix-tree theorem. And I think that's all I want to say today, except I want to give you some of our references. So let me list what each of these references does. So the first two I just mentioned, these are the ones that come up with this least squares solution. And these are very easy papers to read. You could all read them. Every undergraduate could read, every advanced undergraduate could read those papers. It's elementary. So the next two papers are where our matrix-tree, higher matrix-tree formula appears. The first of these papers of ours, it gives a preliminary formula which does not look like the formula I presented. And the second paper redoes our preliminary formula in the kind of symmetrical form. So that's the paper labeled the higher Boltzmann distribution. That paper does a lot more than that, though. It does other things as well. And then the last three papers derive simplicial matrix-tree theorems in some special cases. Well, Lyons does it in general, but his matrix-tree theorem is sort of not recognizable from our point of view. Okay, so that's all I have prepared today, but we're out of time anyway, right? So it's 12 o'clock. So are there any questions?
I just have a comment. It was good treatment of simplicial complexes since algebraic topology is not running in the fall. Thanks for having it so that students can get introduced to it.
Yeah, so I don't know how many of you here have learned about homology before, but if you haven't, this is like an introduction to homology theory. This is not really the most general form of homology theory, because you see, homology theory these are groups or vector spaces or whatever you assign not only to a topological space, but for every map of topological spaces, you want to assign homomorphisms between the homology groups. And with this definition of simplicial homology, I haven't even told you what a map of simplicial complexes, a function between simplicial complexes is. And, so you would have to really kind of work hard to work with simplicial homology when dealing with maps between topological spaces. And simplicial complexes are only a very, very crude, it's sort of a toy model for topological spaces. It's a kind of way of modeling topological spaces as combinatorial objects, right? And there are better ways to do it, though, right, that have better properties. But this was enough for a talk of today. It gives you a flavor, a taste of simplicial complexes. It gave you a taste of homology. It showed you that the classical Kirchhoff matrix-tree theorem generalizes to all dimensions. And so I feel like I've accomplished my task. Any other questions?
Oh, you introduced lattices too, which is pretty cool, since integral representation theory relies quite a bit on lattices. So.
All right. So one other thing, I'm not going to be I'm going to be going on vacation next week for a few days, and so I'm not going to be able to give a talk. I'll be out of town, and so I haven't decided what I'm going to talk about next, and I don't know if I'll be prepared to talk the week after. So I'll keep you informed. I have to think about what I'm talking about next. But in the meantime, if anybody wants to give a talk, please go ahead and contact me, and I'd be happy to accommodate you. At some point, I'm going to run out of material that is presentable to a seminar of this kind, right? Because at some point, it really does get a lot harder to explain research to an audience which hasn't had like the standard complete list of graduate courses, right? So anyway, okay. So other questions? Okay, very good. Thanks for coming. I will look up the formula and correct myself on the YouTube video that I'll be uploading if I need to correct myself. Okay, so
Thank you.
okay, take care.